接下来的场次，我们非常荣幸邀请到演讲嘉宾 Monolithic Power Systems Jinghai Zhou 先生。Jinghai Zhou 先生将为我们带来题为10K 瓦高算力与 PU 供电方案的精彩分享。For our next session, it is our great honor to welcome our speaker, Mr. Jinghai Zhou, SVP, Cloud Computing at Monolithic Power Systems. Mr. Jinghai Zhou will share his insights titled Path Towards 10 Kilowatts and PU Power Delivery. Ladies and gentlemen, please welcome Mr. Jinghai Zhou.
Good afternoon. Wow, look at the crowd. So excited to be here. Today I bring something that all of us want. Take a guess. What do I bring? I bring power. So we're talking about the power, the most important part of the processor performance. And we're here today try to tackle the common technology issues, challenges that we all have. And the path towards high power, say 10 kilowatt xPU power delivery is never going to be an easy path. Now, I remember when I started the journey for this power delivery, I think it's 6, 7 years ago. And at that time, everything is about 200 watt, 300 watt, even at 500 watt. And people think, oh, that's a lot of power. Guess what? December 2022, everything changed. And AI is real. So today, let's look at the curve. What did the AI bring the impact to us? And I think the first thing it comes to us is the grid power. Why electric power is a challenge? This is a well-known curve from semi-analysis. It demonstrates the rapid growth of electricity usage of data centers. And also, it shows it's so unpredictable of the power growth in the future. You can see the very aggressive growth is about 8 times towards the very worst case compared to the best case, right? So it's 8 times bigger. And also, every 3 to 4 years, the power demand will be doubled. Assuming the whole world could actually possibly generate this humongous amount of electricity. How do we refine those crude energy? Think about tens of thousands of volts and into less than 1 volt, and with the millivolt accuracy to the processor. How do we deliver that power precisely to the individual power-hungry processors? Now, this is a chart I compiled last year, actually this time last year. 2025, I put all the ASIC, GPU, TPU, CPU, all of them, plotted the power consumption. And you can see that the worst case, it was about 1.5 kilowatt per processor. And we also predicted, right, for the next 3-4 years, the power demand is going to go all the way, say, 5 kilowatt per process. Guess what? I was wrong. And the data from today, the mid of 2026, you can look at this number. It's already exceeding 2.5 kilowatt per processor. Now use that new data, I predict again, by 2029, one package of the processor gonna exceed 10 kilowatt. Are we ready? Are we ready to deliver 10 kilowatt of power into the package? I want to make an analogy, right? 10 kilowatt, how much power it is. Every household, you have an oven, right? Have a bakery oven. That oven, it's about 1.5 kilowatt. So imagine you pack all of them, 6 of them, into one tiny package, and you still want to deliver the power and to take the heat out of it. So are we ready? This is the path. This is the path to the 10 kilowatt power delivery. And I started the path 5 years ago and started with our key strength. MPS key strength is the monolithic processor. And the processing technology allow us to be really the keystone. Everything else is built around it. Now look at the diversified semiconductor optimization. Then I'm gonna talk about end-to-end power solutions from silicon to total solution. And then how we deliver the solution to our end customers. We make it as a module. And then how do we predict the performance of the overall solution? And we introduce the predictive co-design methodology. And all that together lead us to the high power delivery for the processor. First thing first, in the power semiconductor industry, the power transistors cover a wide range of voltage and the current and operating switching frequencies. So for every application, the usage and optimization steps are very different. For example, the figure of merit of a transistor, of a device, power device, operating at 500 kilohertz could be completely different than the device targeting at 5 megahertz switching frequency. Therefore, the device optimization process has to take a holistic view, and let's get into it. This is a typical power map within a data center rack. So on the very left is the zero stage, and then in the middle, zero stage taking the 800 volt coming is very new for the whole industry. And then everything is coming from 800 volt down to a middle voltage. Either it's a 50 volt or 12 volt, then converted down to the input voltage for the second stage. First, let's look at the input. So as you can see here, the 1200 volt silicon carbide JFET found its home in this hot swap converter. Hot swap circuit need a very robust and super nice SOA, very low RDS(on), and also thermally enhanced package. Those are the key elements for that device. So we have that. And in the middle is a mix, right? There's a zero stage, there's a first stage, and you can see all different semiconductor devices start to come in and try to compete with each other. And I think right now, the 650 volt GaN devices has leading the race, and especially for the 800 volt front end. Then the output of the zero stage, also the input of the first stage, and they're roughly 100 volt to 80 volt, and there's a mix of silicon devices and also GaN devices. Again, the 100 volt GaN devices have an edge, and the reason for that is the switching capability. They're so fast. And the output of the first stage, on the other hand, depends on the output voltage, requires a 40 volt silicon or a 16 volt device. Now, MPS offer a 16 volt smart SR, and that integrates the current sense, the temperature sense, the protection, the drivers, everything built into that. So that can further minimize the size of the device. And the second stage is pretty much dominated by the silicon process. And for example, the monolithic BCD process has a tremendous advantage. So this is a curve I put together based on our own device performance and of course normalized. And you can see the potential of that device voltage rating 16 volt down to 6 volt. If my bus voltage dropped to 6 volt, there's almost 3x performance improvement. 3x. That's why going that direction tremendously help us to reduce the size and improve the efficiency. Now, that's not enough. The reason is, even you have a super nice device, you still need to have a way to package them. So on the right side, you can see the right side, there's a monolithic interface, so-called driver MOS, compared with a discrete die driver MOS. As you can see here, not just the device is smaller, but also all the parasitic inductance and resistance are gone. And the packaging technology is so much easier for the monolithic design. That's why that's the future. Now, we started with monolithic design when a very tiny package, and the whole industry say, no, we want a common footprint. So we have to make the device much bigger at the beginning. That's 5 years ago. But today, the game changed. Everyone's asking for high density. So it's a perfect timing, perfect for a monolithic approach. I'm going to quickly touch those two because end-to-end power delivery solution is our strength. For example, let's go back to this chart. The reason I'm so happy to be a solution provider A to Z, because if I want to know every detail in those blue boxes, every single transistor, how are they connected, how are they controlled, I have the access to that. And that gave us a huge advantage in terms of the next slides I'm going to talk about in terms of the predictive co-design. Once we know the circuit inside out, that allows us to provide our customer a complete view of the solution. Oh, here's another thing, right? Less is more. So what we really want to do, can we get rid of the middle child? Okay, the first stage is gone. And that will make the system efficiency so much better, at least 2 to 3% better by getting rid of the middle guy. So we're going to talk about that. The next thing is you have all the boxes, the blue boxes on the previous page. How are we going to deliver that solution to our customers? So the answer for that is our component integration by modularization. Very simple. The module design concept started many, many years ago, but not until this wave of power density requirement that the module design became a necessity. It's not just something look fancy, but it's a necessity. So to do that, we started with our nickname sandwich module. And on the very left, 0.7 amps per millimeter square. And then we create the L stack, meaning the inductor is on top of the power device. And this one is very popular right now because of the simplicity, but it does have a limitation for that design because you don't have the output capacitor integrated into the L-stack modules. And also, the thermal impedance from the junction, the die, to the top is a little bit challenged. So we create the H-block. H-block module is the one in mass production right now. It's a four-phase design with 1.7 amps per millimeter square. And you can see here, there's a capacitor, array of capacitors. On the top is the input caps, and on the bottom is the output caps. That helps our customer tremendously in their system design. And we didn't stop there. The one is coming out, next one, we call the dual. Take a guess. How many phases do we have on the dual? 8 phases. This is the first industry first 8-phase module. We call the dual H block, also including the capacitors input and output, and it's hitting 2.7 amps per millimeter square. Gen 5, very excited. We have Gen 5 coming up, and I'm going to spend the last 5 minutes to talk about this solution. Also give you guys a quick view of all the stage 0 modules, right? And the 12 kilowatt, oh, don't forget this one, 32 kilowatt. That's the hot swap module on the upper right corner. And then there's 12 kilowatt, and this is 20 kilowatt. And all those are the ecosystem to power the 800 volt DC bus data centers. Now, we talk about the modules. And one advantage of doing module is now we can start to model those modules way ahead of time. Every module we developed, we have a simulation model. We do the correlation step by step, again, down to the transistor level. So it's very, very accurate. And with that, it allows us to do a so-called system twin concept. So today, I'm introducing a system twin. It's a virtual simulation tool, help our customers or even our internal designers to predict the performance of the system. Here's a comparison. 1 year, less than 6 months. And how do we do that? And everyone, if you're in the lab, try to debug the power issues, and you know what I'm talking about. And the power is so black magic, and sometimes everything looks fine. The next day, something doesn't work, right? And because there's so many variables in the power design. Now, on the left side, this is a traditional design cycle. You got the power spec, and design the board, and Gerber out, come back, and some engineers spend weeks of time try to check everything. And then, of course, the list of issues, and you go back and forth. And that takes a very long time. However, with our system twin approach, everything is predicted way before our customer even start their design. We provide the design. The key to that system twin is the accuracy. The concept of simulation is nothing new, but how you make each individual component as accurate as you can. That's the key. Once you put them together, you predict the performance. So how does it go? There are 2 curves. Actually, there are 4 curves. The top is output voltage current, and there's a white line, and there's a blue line. And see how well they match. And this actually is what I'm talking about. System twin has to be a identical twin. Now, we talk about all those 4 pillars. What we're going to do next with all the tools we have. Why are we doing high-frequency MIVR? Sometimes I call it MyVR, but it's M stand for modules, module IVR. There's two paths. One is the processor power demand is so big, and even just the copper along the way, the power path itself has a challenge. The TDC is 10,000 amps. The DIDT is 10 amps per nanosecond. Now, the conduction loss on the PDN, the drop on the L, inductance of the PDN, it all requires us to cut that path as short as possible. That means vertical power delivery, integrated VR is a necessity. On the other hand, because everyone wants to pack so many computing nodes into one standard rack, 1 megawatt. Now, power has to be as compact as possible. The XY dimension need to create 3 amps or millimeter higher, and the height need to be 2 millimeter thinner. To do that, high frequency, integrate all the passive components, active components, and optimize our low voltage process that I mentioned earlier, the 3X figure of merit, and the modularization. So here we have it. So I'm introducing our modular MIVR to the world. This is not a 1.8 volt IVR. And this is not a 3.3 volt either. It's a 6 volt bus optimized IVR. It would take 6 volt from one side and then create a 0.6, 0.8 volt to the other side. Everything's integrated. The power device, the capacitor, and the inductor within that 2 millimeter height. And the thermal design current density, 4 amps. How do we put them together in the system? Here's a cross-section view of the IVR, MIVR systems. And this array of the MIVRs, and there's a copper block to take the heat from the middle IVR to the bottom cold plate. And this is just one implementation. And you can see that power is coming in from one side and shoot the power out from the other side. Now, there's also one little blue block right there. They call it PPU. So what is that? PPU stands for Power Processing Unit. And this is our first 256 phase controller with everything integrated, including the caps, resistors, you name it. And it can control up to 8 rails. So this controller alone is able to deliver, to control total power over 10,000 watts. By the way, the form factor of this controller is the same as the previous MIVR. It's a 6 millimeter by 8 millimeter. So here's an overall view, floor plan of the MIVR system that we're working on. You see the PPU is at the corner, but you can move that PPU anywhere you want. Depends on your power map, right? The ASIC map. Now, I got this question a lot. People saying, why don't you integrate your control, each individual control circuit into your individual MIVR modules that make everything look cleaner? Well, let me explain this. If you have a star connection, you have a controller in the middle, and you star connect to all your power blocks. Is that easier in layout versus a NAT connection? If you don't have this central control, you're going to have a NAT connection because each individual module is going to talk to the other ones, all of them. So it's a lot harder. Not to mention the optimization of the transient performance when you don't have a centralized power processing unit. And we didn't stop there. We also, We also create a MCAP concept. The MCAP is something that same size as the power devices, and you can actually put a deep trench cap in there, or you put a active device in there. So the whole idea is it's modular. You can mix and match with each individual power need in your processor. And I can take this whole thing and make a single vertical power delivery module as well and put on the backside of the motherboard. So it's very versatile. Here's the MCAP performance improvement. You can see that the high frequency impedance drops significantly. And also, remember we used the system twin concept, and this is the result of the system twin. We built a system for 10 kilowatt, and here's the impedance reduction, 6x impedance reduction by using this MIVR systems. Yeah, so this is basically it. You have a system, you have a PDB, 20 kilowatt, 2 processors. On this side is an explosive view of how we do that. 2 processors, the thermal copper bar, and then see all the individual blocks built in. Like I said again, you can move those on the back side if you want. Depends on your system implementations. We can't do this by ourselves. We need partners. So this is why I list all this call to action. We need a high frequency magnetics. We need to work on the low ESL, ESR capacitors. And also PCB is critical, low CTE PCBs, and passive active embedded technology. We want a common footprint ecosystem. So at MPS, we're not just powering processors, we're powering possibilities. And so join us to do the impossibles. Thank you all.